Okay, let's get started. So on Tuesday, we talked about the 32-bit version of x86 CPU. We talked about their registers. So today, we're going to extend that to the 64-bit version, which is the version most of you are using. Some of you are using Mac and one and two architecture, but that is also a 64-bit version of CPU. So we already said this figure before. So there are many different groups of registers: general registers, configuration registers, debug registers, system registers. Then for multimedia, there are the multimedia registers for floating computations. But now we have other different architectures like GPU, TPU for float number computation, which will do an even better job than the CPU. So the 64-bit version is actually not much different from the 32-bit version. If you look at the instruction set, if you look at the assembly language level, just the register names are different. They have the 64-bit version, 32-bit version, and backward compatible with the CPUs back in the 70s or 80s. So we will look at several concrete examples today. So we kind of looked at this before, so you know what's going on here. So move, that's the instruction move. And we have Q here, means we are moving 64-bit, 8 bytes. So last class, we're talking about move L, which is long 4 bytes. So the first operand is the source, the second operand is the destination. So we're moving from the first one to the second one. So move is not really move, it's more like a copy, right? So the second instruction here, we're moving a concrete value, immediate value or constant to RAX. So this value is not anywhere in the memory, right? So this value is hard-coded in this instruction. The instruction itself is in the memory. The part of that is the value. Then we're moving from RBX to RAX. So this instruction itself, when CPU executes this instruction, the CPU doesn't need to refer to the memory. Want to retrieve this whole thing to execute it. This whole thing is stored in the memory. So it will retrieve it, then execute it. So this is just in the memory during execution. So this is super fast. Then we have RSP. S is stack pointer. So here we have a pair of parentheses here, which means the first operand is a memory. Okay? The memory location is in the register RSP. So we're reading something from the stack here, actually. We're copying something from the stack, which is part of memory, to the register RAX. So this instruction is a little bit slower than the previous one, because this one happens in the CPU. This one is moving data from memory to CPU. That's why it's slower. So main memory is not part of the CPU. However, there are a lot of optimizations at the CPU level. And we have caches. So when you move something like this, maybe the data is already put in the cache. It's already in the CPU. So the move will still be very fast. So this one is similar. We're moving from stack, but not where RSP points to. It's RBP points to -8. So we saw this one before. So we have base, we have index, we have the size of each item there. So this is the same syntax as the 16-bit version. Okay, so let's do this again. So the first instruction, the $ means that's a constant value. Move some value to RX. What does the second instruction do? And how big is the data we're moving here? Second instruction.
There's 4 bytes in memory address.
Okay, so yeah, right there, we're moving something from we're moving something to the memory. Okay, and because the second operand is the destination in this syntax, and that address is in RAX. That's right. But how big is this thing? You said 4 bytes, right? Why do you think it's 4 bytes?
the suffix Q is fine.
Yeah, Q is, so here, Q means one word, and each word is 2 bytes. So Q means 8 bytes. Yeah, so if you want to move 4 bytes, you will use move A. Then the RAX itself, this is also 8 bytes, 64 bits. The third instruction, this is simple, just move RAX to RDX or copy RAX to RDX. This one, how about this one? It's similar to the second one. Anyone? Go ahead.
Move an 8 byte
Okay.
value in REX to the memory location in RDX.
Yes. So the memory address is in RDX. So we're moving from register to the main memory. So the next one is the reverse. We're moving something from memory to the register RDX. So those are those instructions. So if you look at the C or high level language equivalent of this, we're looking at something like this. We're assign this number forward to this register. Then we're moving this. So this one is kind of like a dereference. So RAX is that address, right? It's a register, and in that register, what we say is a value, and that value has some meaning. That's the address. Okay. Then we're moving something to that address at C code level. It's like we have a pointer. I know we haven't talked about C yet. We're going to talk about that in 2 weeks actually. So we have a pointer. Then we are dereferencing that pointer. Use a star here. We're dereferencing that and assign value to that address. This one is just a simple copy. This is another dereference because we are, and it's a write dereference. The last one is a read dereference. We are reading from an address and load that to a register. So in the 64-bit version, we reserve some general registers, same as we reserve in the 32-bit version. 32-bit version, we reserve EBP, ESP, right? SP, S means stack pointer. BP, B means base pointer. So 64-bit version, we also reserve RSP and RBP. So reserve here means there are some rules for the developers of compilers, OS, and also CPU developers, they agree. We are going to use those registers for some special purposes. So RSP will keep track of where the stack is. Okay. So stack goes down. We will talk about what stack is next week with more details. So RSP always points to the top of the stack. So which means the value in the register RSP is also an address. Then we have RDI, RSI, RDX. So those are reserved for function arguments. So we're going to see a very concrete example later. In 64-bit version, we use those registers to pass parameters. In 64-bit, in 32-bit version, we use the stack, and the stack is on the memory, right? So if you pass parameters, use the memory, it will be much slower than just pass the parameters using registers. And we use the register RAX to store the return value. So in C programming, one function can have one return value, right? But actually, a function can return more. So some of you have been programming in C. So how do you return more things in C? There is only the syntax of C only allow one return value. But if you want to change something more, how do you do that? So the parameter you give can be an address. The address points to a memory, and you can change whatever there, right? So that will be also an output of this function. So the return address is also called the type of that function, and that is stored in the register AX, or 32-bit version in the register EAX. So let's say here we have one example. So this is a system call. This system call is called write. System call is an interface OS exposed to the application. So the syswrite is actually the system call's function name in the kernel. And when you write something, you need to specify what file descriptor you're writing to. when you program in C or Java, when you open a file, you use fopen or open. Eventually, that function becomes a system call for open. So after you open that, you can do a system call to write something to that file. Then you close that, right? So this is after you open a file. So the first parameter for this write is we need to know where we're writing to, and that is identified by the file descriptor, the FD, which is just an integer. Then you need to specify where is the source of the data you want to write to that file. Okay, and that source obviously should be in the memory. Okay, then how do you indicate a piece of memory? These are the address of that memory and also the size of it, right? So the second parameter is actually a pointer, which is an address. Then the third parameter is just the size t, which is an integer. So in this case, we have 3 parameters for that system call, and all of them actually will be passed to that function write using those registers. The first parameter go to the register RDI, the second one go to RSI, the second one go to RDX. In a 64-bit version machine, we can have, I believe it's 6 registers we can use to pass parameters. But for 32-bit machine, we use a stack to do that. Then of course, we have RIP, the program counter. We've been talking about this multiple times. Then there are several other general purpose registers. They do not exist in the 32-bit version from R8 to R15. So let's talk about a little bit about the calling convention. We will revisit this later as well. So when you're programming C, there's something called a calling convention. It defines, especially for the compiler, how the compiler will implement that function. It defines whose job to do what. Okay. Eventually, we're going to use the call instruction, push instruction, return instruction. But who is supposed to do what? Right. So in the 32-bit version, we have this calling convention called C declare. So in this rule, we have a caller, and the caller has the job to push the arguments, the parameters, to the stack, and in the right to left order. Okay. So let's say we have a function 1. Let's say we have a C function 1, which is f, and f takes 2 parameters, a and b. This is a function. We do not care about the implementation of this function. Then we have another function, g. G takes just 1 parameter, let's say a. Then what will g do is, g will just call function f, and it will use 1 and maybe like this. So in this case, g is the caller, and f is the callee. Okay. So function g, eventually, it may run something here, it may run something after f, but eventually function g will call function f. So g is the caller, f is the callee. So it's g's job, function g's job, to push the parameters of this invocation of f to the stack. It's g's job to do that. But as a programmer, you never did that, right? So when we say it's g's job, means the compiler will do the job. Compiler will generate the code to make sure g will push the parameters a and 1 to the stack from in the right to left order. So we push a first, then we push 1. Then function g, there will be an instruction call to eventually make the jump to the function f. So after the f will also push previous base pointers onto the stack and set up its own base pointer, create a space for its own stack, and make sure the stack is consistent when it returns. So when function f returns, it needs to make sure the stack is balanced, and also there is a return instruction at the end of function g f, and also return instruction as a function of G as well, because someone else will also call G, right? Some function will also call G. And the return value should always be stored in the register EAX in 32-bit or 64-bit will be RAX. So those are the calling conventions. However, the 64-bit version, the calling convention is a little bit different. So we do not use stack to pass the parameters anymore. We use 6 different registers to do that. RDI, RSI, RDX, XAX, R8, and R9. And the benefit of doing that is it's much faster. Previously, we're going to push something to the stack. Stack is memory. Then after you push, you need to access that. So that's 2 memory accesses. Very slow. But here we're moving something to register, then we can directly operate on that. It will be much faster. So we're going to use this code as an example to say how the 64-bit version is different from the 32-bit version. So this is the same piece of C code. We are just going to compile it using 2 different commands, and one output will be 64-bit version, another output will be 32-bit version. So you can see the options we're using here are almost the same, except this one, dash M32. Okay, so when we give this to GCC or LLVM, it means we are going to generate a 32-bit version of this executable. And this is the name of the executable. Land here, land 64. But they are generated from the same source code, this source code. So let's see what this piece of code is doing. We have a main function. When we develop a C application, we always have a main function. I talked about this last week. The C standard library will have underscore C main function to call your main function. For the developer, this is what it does. So we define 2 local variables, A and B. So the size of them are long, which is 64 bits. So no matter you compare this into 32-bit machine or 64-bit machine, those 2 variables will be 8 bytes. Okay. Then we compare how many arguments we are giving to this program. So this is a command line program, and you can give command line arguments to it. We compare if there are 3 command line arguments. If not, we just print out the usage, then just the return. So after this program will just exit the main program. If there are 3 arguments, the first argument will be the name of the program. So you give 2 integers there. Then you print out the size of long is how many bytes for this architecture. Actually, no matter 32-bit or 64-bit, this should always print out 8 bytes. So we're going to change the first 8 bytes to an integer. So we use a function a to ll to do that. Also change the second to an integer. Because what you input there is actually a string. It's not an integer. We change those to integer, and we just add them together. So here we're add them together. However, we're using a function to add them together, not directly adding them. We're using the function ladd to add them together. So we have 2 different C program of this. This is also part of the main C. So we only have 1 C file here. So here we have a C function called ladd. The return of this type is long, 8 bytes. The input is the first input. The parameter is a pointer. Okay, so the star here means this is a pointer. This is an address. And the name of this variable is XP. The type of the variable is a pointer. And what we are pointing to? We're pointing to long, which means we're pointing to 8 bytes. Okay. And the pointer is just the address. Then here we have long y. So this one is not a pointer, it's just a value. Okay. So that's why the first parameter here, we are giving the address of A instead of A. The second parameter, we're using the value of B. Okay. So in programming language, this is called passing by address or passing by reference or passing by value. Then we just add them together. So here we dereference the first parameter, and so So we get a long, then we add them together with the second parameter. That's it. Okay. So if we compile this, let's try to compile this on my computer. So this is exactly the same say source code here. The code we just look at. Then let's take a look at our makefile. So makefile is where you can specify your commands, how to compile the program. So we have two different makefile commands here. The first one is this. Here we have a dash M32. We're getting a 32-bit version of this file, and here we're getting to a 64-bit version file. So let's just compile this by doing make. Oops. We do a make all here, so we compile this. We actually already have that. So now on this side, we should have 32-bit version of this program, and you can say we do a file on it, and they tell us this is the 32-bit version of the program compiled for Intel architecture. There are symbols of that. Let's get another one, I guess. We should have a 64 version of it as well. So this is the program compiled from the same C code. However, this is the 64-bit version of it. Then let's compare this by comparing the instructions. Let's do a obj dump. We can do a dash D here. Then we do a 64-bit version first. We are looking for the main function. Let's first look at the land function first. Land function. Oh, here. This is the land function. This is the land function. So remember what we did at the second level. We set two parameters. First one is the address. The second one is the value itself. So we are dereferencing the address from to get the first value, then add that with the second value. Then we just return, right? That's it. So after we compile this, there are only 4 instructions here actually. The last one doesn't really matter because at this point you already returned. So the last one is not necessarily a valid instruction. The decompiler, the disassembler probably by mistake thinks this is an instruction. The first instruction is called NBR64. This instruction is 4 bytes. Those are the 4 bytes of this instruction. So this instruction is related to security, and we're not really using this in this class, so we can skip this one. The second instruction, what we're doing is we're moving the value in the memory, and the address is RDI to the register RAX. So what are we doing here? Let me make this bigger. What are we doing here? What is the RDI? It's a register, right? Anyone remember what is stored in RDI? During a function call, which is called a reporting convention. Yes, the first argument. And what is the first argument? Memory address. That's why we have this parenthesis here, because when dereferencing that memory address, we're moving what is either memory address 8 bytes to the register RAX. Okay. So after this instruction, the first value is in register RAX. Then the second instruction is just add RSI to RAX. So what is RSI? So RDI is for the first argument. RSI is for the second argument, right? So we're directly adding RSI to RAX. That's it. Then we're done. Because we wanted the return value in the register RAX, and it is already in RAX. That's it, right? Then we just return. So this is a 64-bit version of this code. Only technically 3 instructions. If we look at the main function, the main function is a little bit big, so we will only look at the call to, where is the call to? So this is a print. So this, so here we have a call. This is another call. This is the call to this. Oh, this one actually optimized it away. So this is interesting. We're going to change the makefile a little bit to say this. This is actually very interesting. You say here, we used that ATLM function, that's a library function, to change from string to integer. We did it twice, right? There are 2 inputs. So after that, we didn't really call the math function here. That's because it was optimized away. So let's change the makefile a little bit. Let's go to research. I think it optimized it away, so we're going to use so here we're using O2 here. So that's optimization level. Let's change it to O0. That should do it. Okay, let's do this again to say if the main function has been changed. What's going on? Let's take a look at the 32-bit. Maybe confused what's going on with this. So obj.d 32-bit version. So let's first look at the land function in the 32-bit version. First of all, you can see it's a little bit longer. It has 6 instructions instead of 3 instructions. The first instruction is move something where ESP points to, ESP +4 points to register EAX. So how many bytes we are moving here, this instruction? The destination is only 4 bytes, right? So we can only move 4 bytes. But the data we are giving to that function at the cycle level is 8 bytes, which means a single instruction will not be able to move that 8 bytes. we need two instructions to do that. So the first instruction is actually dereferencing the address. So we are getting ESP +4, the value there, which is the first argument, to the register EAX. Then we dereference that again to get the value EDX. And this one is +4. Then this one with no +4 can also get EAX. So by doing this, and also this one, we are getting the lower. So we are adding two 64-bit numbers together. But our register is only 32-bit long, which means we need to add twice. We're adding the lower 32-bit first, the carry, if there is carry, then we're going to do that to the second addition, which is the higher 32-bit. So the result will here be 64-bit. If there's a carry typically 65-bit, the result will be stored in two registers, it cannot be in one register, right? Then that's why we have the first addition here with the destination is EAX. The second is not really a regular add instruction, it's an ADC instruction, addition with carry. So we will consider the carry from the lower 32 bits addition, and the result will be in register EDX. So the return value in this case are both in register EAX and register EDX. Okay, the lower 32 bits in EAX, the higher 32 bits in EDX. Then let's look at the main function here. So this is the main function. So you see what's going on. We do not have a call to the land function, right? So here we have the translation, then we adjust output. We don't have the call to the land function. So what happens is here, we have the addition here. So the compiler is not really faithful to us in this case. In our source code, we have two functions, the main function, the land function. We ask the main function to call the land function to get the result. But the compiler actually put the value, the instructions of the land function here, because they are so small. They're just the 6 instructions, 3 instructions. They embedded here, they ignite here. By doing this, they make the program run even a little bit faster. So this is what the compiler did there. Any questions so far? So we already compared this. Okay, so besides x86 and x86-64, I also want to introduce you to some other architectures. So we will talk about ARM. So our research are mainly on ARM. So there are two very popular ARM architectures. One is Cortex-A. This is what your Mac has, and also your phone has. So you are using your main CPU is the Cortex-A CPU. Then on your phone, there are also multiple Cortex-M CPU, which we'll talk about. So the ARM architecture and also RISC-V and MIPS, so they follow the idea of a reduced instruction set philosophy, which means their instructions are very simple. They are going to do very simple things. They're not going to do addition of a register to a memory. There's no instructions like that. So all the additions will be just the additions on registers, which means if you want to do addition, you have to load something from the memory. Then you will separate that into multiple instructions instead of one instruction in the Intel architecture. So that's why it's called the reduced instruction set. So you can see, because the execution units, decoding units are simpler, they have much more room for general registers. So the 64-bit version will have 6 general registers or 8. Then the 64-bit version of Intel will have more, 16. general registers. But for ARM, which is a much smaller CPU on a mobile device, we have many more general registers. Here we are looking at least 31 general registers. Okay. Double the number of general registers in Intel architecture. And all those are just the system registers for different purposes, privilege levels. So this is a Cortex-A. So here is a much more simpler version of Cortex-A, which is called Cortex-M. This is used in all kinds of low-end IoT devices. On your phone, there probably are multiple Cortex-M CPUs, but the main CPU is Cortex-A. In your car, if you have a relatively modern car, there are probably hundreds of Cortex-M CPUs. Okay. So I think ARM has a report last year saying that there are 250 billions of Cortex-M CPUs in the world already. Okay. So a huge number of them. And this CPU, they only have 12 general registers, but still compared to x86, that's more. Those three are actually special registers, so there are some other special registers as well. So those are for the ARMs. Any questions? Good. Then let's take a look at some other assembly example. So in your assignment, you are going to do 64-bit Intel assembly. When we read code for the OS, we are going to read a 32-bit version, which is easier. So here, I have a little bit challenge for you. We have a mystery function programmed in C. The name of the function is mystery. There are two parameters. One is A, name is A, second is B, but we don't know the type of it. Okay. You need to figure out what's the type of A and what's the type of B. And this function doesn't really return anything, so its return value is just void. Okay, which means the value in the register RAX doesn't really matter in return because the function doesn't set that. Then the function only has 4 instructions, 5 instructions including return. Then let's say, what is this function doing? First instruction, we are moving something from memory. The memory address is in RDI to register RAX. Okay, so what is RDI? Yeah, first argument, RDI, first argument, RSI, second argument, right? So which means RDI is this A, okay? And we are dereferencing this using parentheses, which means A is what? A is a pointer, A is an address for sure, but we don't know what it points to yet. But very likely it's going to be something 8 bytes, right, in this case. Then the second instruction, RSI, which is the second argument, we're doing the same thing. So RSI is B. And there's a parenthesis, which means B is also an address. We're moving where B points to RDX. So now we know that both of them are just pointers, address. Then the third instruction, we are moving RDX. What is RDX? Okay, so which is the second, the value, the value B points to, basically, right? Okay. We're moving that to where RDI points to in memory. What is that doing? What is RDI? RDI is the first address. Yes. Then the next instruction is moving the value of B to, so actually moving the value A to where B points to. Yeah. So basically this function, what it does is the input is 2 memory addresses. Then we're going to swap the value and those 2 memory addresses. That's it. So state code level, it will be something like this. So long here is also 64 bits. So we have a pointer. Then we're going to swap them. So at a state code level, you can see we actually need a temp variable here, right? Yeah, so here we actually have two temp variables, T0 and T1. And those temp variables will be stored in memory, or they can be optimized away. At state code level, you don't need to consider that. At state code level, you consider, oh, we have two temp variables, and we're getting the value from address A and from the B, then we swap them. Okay. So after you compile, the compiler actually moved away the temp variable. We do not say any sign of temp variable. Right? The compiler very smart. We do not need to create those. There are many other arithmetic instructions. We kind of covered that Tuesday, talking about 32-bit, 64-bit the same. We have addition, subtraction, integer multiply. We have shift. So for a value, if you shift left 1 bit, means you actually multiply 2 to that value. Then you can also shift it to right. Then you are divided by 2, right, because it's a binary value. So when you shift, you can also consider the carry flag. That's why there are several different shift instructions. We have exclusive OR instruction. We saw one of those instructions Tuesday. We exclusive OR the same register, right? So no matter what value that register has, after the exclusive OR, it will be value 0. So we are basically clear that register. But why we're not doing a move there? So what we can do is to say we can do something like a move value 0 to the register EAX. This is equivalent to the character to do an exclusive OR EAX. So those two instructions, they are actually equivalent. After this one, the register EAX will have the value 0. And why the compiler is choosing this instruction instead of this one? That's because this instruction may be longer. This instruction could be 4 bytes or 5 bytes, I think. This instruction will only be 1 byte. So actually, we can do a little test here. Let's just Google online assembler x86. I'm not sure if this one is blocked by it works. Let's say we want to do a move. This is probably Intel syntax. So here it says this is Intel syntax. I'm going to change this a little bit. We're going to move to EAX value 0 here. So if we assemble this, this website is blocked by the university. Yeah, let's change to another website. This one. Oh, this one should work. Assembly. What we can do is, here is code. So just do a simple. This is also Intel syntax. Looks like we do a move EAX 0. Then we also do a exclusive OR EAX EAX. Then we assemble this. Up here, assembly. Where do I say that? Sorry about that. I don't want to do it locally because it will be much more complicated. Let's see. Yeah, let's just do it locally on my computer. Okay, so we don't really need this part. What we really want is move EAX 0 and exclusive or EAX. So we do AS. Yes. AS. Let's do GCC. Damn. Okay. So the online tool I usually use is somehow blocked here. This one is the one I use, but there should be other ones. Does anyone know a good tool here? Let's see this one. This one here. X0. This is a compile. So it's not showing us binary. I'm sorry about that. Let me get it back to you guys later on Piazza about this one. The online tool, because we use that for hacking, so I think no system blocked that website. Yes, that's a website we use to write exploits. So anyway, the main reason the compiler is choosing this over this is because size. So here, even this data is right. This is 4 bytes of data. So means that this part will be 4 bytes. But this one is not hard into anything in the instruction, so it can be very small. So another exercise, let's say we have a say statement. We have two variables A and B. We are adding B to A, then times B. Then we assign a value to C. So how do we write this in assembly? It will be something like this. We are going to move the value A to RAX. Obviously, at assembly level, this value A should be at some memory address. So in our parentheses. Then we're moving value B to RBX. Then we're adding them together using the AND instruction. Then the result will be in register RAX. So after that, we're going to do a multiplication here, integer multiplication here. And this instruction actually only take one argument, which is one of the number you want to multiply. Then it implicitly it will use RAX for the second value. Okay, that's why in this instruction you do not say RAX here. It's implied there. We're going to multiply RAX and RBX. Now after that, the value will still go back to RAX. So we will move the value eventually for RAX to the variable C. And those variables, they could be at different memory locations, memory addresses. So this is how you implement. So one statement eventually becomes 5, 6 instructions. We also talked about those instructions. INC is increment, which means +1, decrement, and they get the negative value and they get the logic, not value of that. So those are other registers. Then if we look at a piece of C code that is eventually compiled into assembly, it will look like something like this. We keep some kind of file information here. Text means the following is instructions. This is code section. Text means code section. Then there is a global symbol, the main function. Then we want to align the stack to this side. The main function is a function. Then there are some other directives. This setI means control frame information related to the stack. Then the very first instruction is actually this one, push RBP. We are saving the value of RBP. We will talk about this next week, why we're doing this. Then after that, we have move RSP to RBP. Okay. So here we are overwriting the value in RBP with the value in RSP. Okay. Because we're overwriting, we want to save this value. Okay. Because this value is still useful. How do we save it? We save it in the memory. We push instruction to do that. Then after that, we just have puts and other functions. So this is what assembly. So if you write assembly, it will look like something like this. Oh, CFI is code frame information. There are many places you can learn this. First of all, we give you a book to read, which is Dive into Systems. There are section 6 and section 7 you should read. If you want to learn more about this, everything is actually in the Intel architecture manual. This manual is like 10,000 pages. Okay. It has everything about the microarchitecture level and the instruction set level. So a better way to learn right now is to just use large language models and also Google. This is like one page of that document. There are several different volumes. One volume is talking about instruction set, and that is probably thousands of pages. Then there's also talking about the architecture. So every CPU, ARM, MIPS, RISC-V, they will have a document like this. So this is mainly for people who develop compilers, because compiler developers' job is to translate C code into assembly, and also operating system developers or firmware developers, because you need to directly modify the instruction to manipulate the CPU. Comparison instructions, we talked a little bit about this as well. Let's show you some examples. This one. So at C code level, high level code level, we have a predicate x greater than y. Okay, this is a predicate. So this statement eventually becomes a binary, either true or false. So if this is true, then we're going to do this. Result will be x minus y. Otherwise, the result will be y minus x. So what we're trying to do in this statement, of course, 4 lines of code. So if x is greater than y, we are going to use we will do x minus y, right? So what is the value? It's a positive value, right? So if x is less than y, we're going to do y minus x. So we're basically trying to get the absolute distance between those numbers, right? That's it. Then how does this compare to instructions? So let's say we have those two are parameters to this function. So this function is called absolute difference. The result here is actually a global variable. Global variable could be in memory, it could be in register in this case. I think in this case, it will be in register IX because eventually we're going to return it. So here we actually should have a return statement here. So the very first instruction we do is we compare those two arguments. And those two arguments are, the value of them are in RSI and RBI already. Okay? The value, not the address. Here we're not passing the address, the value. Then if, after this compare, not going to change the value in either of those two registers. What we're going to change, we're going to change the flag registers, the B flag or R flag registers. Then there is jump less or equal compared to the jump. This is a conditional jump. So if we take this jump, we're going here. We're skipping those instructions. If we do not take this jump, we keep executing here. Okay. So if we keep executing here, we just move those one of the values to RAX, then we use subtract to do that. Okay. Then we do return. After return, the whole function returns. So the CPU will not keep executing. Okay. So this is one branch. This is basically the red branch of the code. However, if X is less than Y or X is equal to, in this case, is less or equal to Y, then we're going to take this jump, then we're going to here. And here, we're going to do a move, then subtract, then also return. So that's why this function has two returns, because we have two ending branches there. Okay, one more example. This is another mystery function. What does it do? Only 4 instructions. The first one is just to move 0 to register RAX. And we have a mystery column here. This is a label, okay? So at machine code level, eventually we don't have something like a label. This eventually, after you assemble this, becomes an address. So here we have INC, the instruction we just talked about, increment. Increment RAX. What does that do? Just add 1. So we initialize this RAX to 0, and here we are adding it to 1, right? Then we are going to compare 5 to RAX. Okay? Then if it's X is less than 5, we are going to do a conditional jump. So where do we jump to? We jump to mystery. So where is mystery? Mystery is actually this instruction, right? So if this is less than 5, we're going to, so if this is less than 5, what is the next instruction we're going to execute? Yes, so what is instruction? Because mystery is not really an instruction, right? That address. What's an instruction? Yes, that's an increment instruction. So increment will do +1 again. Now, what is this piece of code doing? We're going to do, right? How many times?
So the R is 6.
So here is less. So the loop actually is 5 times. Because here we're add 1, right? So every time we add 1, so we're going to add 5 times. So yeah. Okay. State code level, it could look like something like this. We have a ton local variable, then we use a while loop to do this. So that's all I have for this week. So far, any questions? Then I will give you guys some time to work on assignment 1, and then I will work around with you now. Yeah, go ahead. Let me find the online assembly. Yep.
Was it deliverable for this part of the summer? Is it okay if I like separate which command this is representing? Like this is the last.
Oh, you don't have to.
I don't have
You don't have to,
Oh,
yeah,
okay.
because it will be very clear to us what's going on.
And also, is it okay for if I just like do those commands and bring together?
So do you know what is the meaning of this?
Yeah.
That's a part.
Right.
Yeah, you can do that.
So I can do that for like two.
I'm Bennett.
Yeah, but this is different from doing 2 commands at
How you
at
think
once.
so far about?
So there are many different things.
It is, well, see, I think I always start to understand, right?
Bro, I feel like it's spikes today, like the difficulty just went.
I know, I think it's always great on the first day. And then I was trying to take the notes on the first day, and I stopped because it was like, oh, we can do it.
Yeah.
I think it's just bad for me to listen, but then like listening also like,
Yeah.
without the air.
This one, we're in the ink. Yeah, this one where.
Yeah, I think.
Quick question, so for interpretation, this is what I have for editable PNG. This is fine, right? This is within, so this is
Yeah,
within.
PNG is fine.
And then there's the code. And then this was a little, like weird to me. So repo, you just want to see all the commits, right? But like, it doesn't include the one where I include repo, because that wouldn't make any sense if I like take a picture and then try to commit it and then take a picture again.
What do you mean by repo here?
And so like, you just want a snapshot of the commits, right? For repo.
Yeah, this is okay, yeah.
Oh, this is okay, because it doesn't include the commit where I added repo, like this is the only editor, so you see updated. So I had to change it because, someone entered in the Piazza, so I changed it, so all I have, the last commit was just edited, updated in the editor, but it doesn't contain repo because I haven't taken a snapshot yet, so this is good.
Yeah, this is good, but we actually wanted you guys to use the command line, but looks like you are using the web version, right?
Like committing stuff? No, I committed through the terminal.
Even this one is terminal?
No, so this
This
is, through
part,
Git- no,
this
this
part
is through
is like
GitHub.
your web, right, GitHub.
So do you want a screenshot of the GitHub commits? Because that's what I thought,
Yeah.
and then, so are you saying you want me to show the like the commits I have on?
We want to say the Git commits, that's better than the GitHub commits, that's a little bit different, okay? So GitHub is based on Git.
Yeah,
Git is an open source tool.
yeah.
Right, so GitHub is like a whole web-based ecosystem based on Git.
Yeah, so I get,
Yeah.
I get add, get push all through the
Okay.
terminal.
Yeah,
but,
that's fine.
For the snapshot, I want to show you the
Yeah,
commits here,
That's,
because,
that's fine, but it looks like those 1, 2, 3, 4, 5, those ones you were added, you committed it through website, right? Because there is verified. So usually GitHub will show verified if you committed through website.
oh, so
Yeah.
this?
Yeah.
These images, I didn't know how to commit the images.
Oh, it's the same. Okay. You
Is it?
use, so what you do is you have a local folder
Yeah.
or you are using a code space. Which one you are using?
Code space.
Code space. Even in code space, you need to upload the image to your folder first.
Mhm.
Then you can edit there.
Oh, so that's where I was
Yeah.
confused, because on the code space, like, I try to add the PNG files
Okay.
in there, but like, it wouldn't let me.
I
Like,
see.
it just like, I
Okay.
couldn't find the file either because it was on the local code
I
space.
see.
So I was
That's
so
what,
confused.
that's
And then
why-
so the only way I added the commits for the PNGs were just through GitHub here, but
Okay.
everything else was just through the terminal.
another way to do this is
Uh-huh.
just to do a git clone to your local computer,
Okay.
then add things there,
Uh-huh.
then you can do git add, then you
Okay.
can push. Yeah,
So do you want me to change?
that
this?
would be better, yeah,
Okay, okay.
yeah.
Okay.
So the purpose is not to confuse the TA, so.
Okay.
I took this class over the summer.
Yeah.
I went through and it seems like my GitHub didn't get reset for the starter assignment.
Okay,
So these are all the old ones. I made a Piazza post, but it didn't get replied to. I think a few days ago.
so when you do a Piazza, could you give us your ID there? Because
I-
Piazza is
that's prob-
anonymous, right?
Okay, that's probably.
Yeah, so what you can do is you can email me, so we can reset everything.
Okay,
So you already have that, right? So what do you want to do? You want to
just reset it all probably.
means we delete all those. I think actually you can reuse them.
Oh, really?
Can you? I mean, you,
I mean, it still has some of the stuff,
yeah,
but
if you want, I would say you can reuse them.
oh, really?
You don't have to start from scratch.
But I don't see my first assignment, because the first assignment wasn't on GitHub. like
Okay.
my assignment, so
Yeah.
If I could, I'll send you an email with more details.
Okay, yeah.
All right.
Yeah, I think you can reuse. I'm totally fine with that.
All right, perfect.
Professor, I couldn't find the presentation.
Slides yet? Yeah, I haven't uploaded
Oh,
it yet. Yeah, I will upload tonight.
thank you.
Mm.
And I had another question about the repo PNG.
Yeah.
Would this be okay as a screenshot?
So, yeah, I think this is funny. Yeah.
Oh, was there any other alternative that you had in mind?
What did you ask for? Oh, finally, I think this tool works.
It says this, GitHub interface the screen.
Oh, yeah, that's fine.
So this
Yeah,
is fine, right?
yeah, this is fine. Yeah.
I also had another question about the editor screenshot.
Mhm.
So should we have this screenshot? Or
Yeah,
is the
This is
final,
fine.
so this is fine, right?
Yeah.
Not the one with the for loop.
Which
Because,
one?
so like, I think there were two instructions, like one said that we just had to have a name and email,
Mhm.
and then later we had to make it printed 20 times using a for loop.
Okay.
So the screenshot that I've submitted does not have the loop.
Okay.
But
Editor one, PNG one,
Oh.
right? Yeah, as long as it's clear to the PA.
Yeah. thank you.
So it looks like Northeastern is blocking all the online assemblers. That's what I want to show you guys, but yeah.
I just have one question. So after doing the homework, I went back and I realized that CD and locate, they don't have a man page, right? I did the update, like, I got the man page for locate, but either way, when I was doing the assignment, when I did man CD, man locate, it gave me an error message. So I went back and deleted those 3 lines from my deliverable.
Mhm.
Is it okay if I like,
Yeah,
after committing
that's-
that,
that's
because then it'll include like the unit that I have.
Yep, that's fine.
Okay.
So do you know why there is no man page for CD?
CD is not a, like an operation.
It's not a program.
Yeah, sorry.
So when you do other things, you do a LS or whatever,
Yeah.
you are, so you're typing in something called a shell, right?
Right.
So you guys will develop a shell later. So when you type LS, actually a program for LS
Yeah.
will be created, the process will be created. A CD is not creating any program. It's actually a special command for the shell itself.
Okay.
Yeah.
All right, perfect. And one last question. So, I. Yeah, so within our, like our homework, when we had to run these different commands, I ran all of these commands, but when I was doing this and how to sort all these files or like whatever, you need a sample file, right? As well, like this is the file I worked with, like I echoed this into a text file.
Yep.
And I was sorting it.
Yep.
So I can do it in my submission.
Wait,
Thanks.
one of them went to. We have heard, we heard from someone else who thinks this thing.
I just wanna confirm something about, deliverables.
Yeah.
So part of it asks for, to modify the LLC file to, print your first name, new line, email address, new line, right?
Mhm.
By new line, do you just mean, I wasn't sure exactly what this meant, so like,
Mhm.
do you mean like just like, first name and then like new line, like email, or do you mean?
Like this.
Okay.
New line is just a slash n.
Mhm.
Yeah.
Yeah, okay.
Yeah.
It's actually.
So, is it okay, then can I just like, I already made like a add comment, can I just make another one?
Yes,
The correct-
definitely.
Okay,
Mhm.
and, just, for the screenshot, also using the editor, is this what you're looking for? This is just, there.
That's
What
fine.
is,
Okay.
oh, is that like?
Alright, thank you.
Yeah.
So, so the stack register we're talking about is actually a stack pointer, right? SP, stack pointer register. In all the architectures, I think we all have a similar register. We probably call it a different name. In x86, we call it the ESP, stack pointer. In ARM, we call it link register, but the purpose is the same. Okay. In ARM, we also call it SP actually, stack pointer, but we have a link register for the BP, yeah, the different name. Then we actually will talk about this next week. So stack is a very fundamental data structure that we will use a lot. And to maintain the stack, we need several hardware support to do that. That's why we have registered to do that.
I don't know.
Mhm. Yeah, the frame, the concept we're talking about is called stack frame. It basically means, let's say, we have function F, we have function G, function G calls function F. Then we're talking about two different versions. One is calling another. Then each function have their own stack frame there, and we will go down.
Yeah, I know what that's.
Yeah. And let's say
You're right.
function F can call itself.
Like my parents are trying to.
We can do a
because
recursive
it's
function
like,
call,
standard
right?
very
Then there will
because
be.
it's like close to
each
job
function
market.
call will have a stack.
Like, like this from my house.
Source code
That's
level, you
literally-
have one
that's
function, the standard, the runtime, you have many.
How'd you get out your first try?
And the size, what's the between
Mhm.
64 and ARM64?
AR64 is the ARM architecture.
Bullets were one of the.
So if you search AR64, that's ARM, that's not Intel. AMD 64,
I mean, ARM64.
Exactly first.
it's called AR64. Yeah, that's its name.
Oh, same, okay.
That's its name, yeah.
Okay, then how to compile that
Okay.
to the program?
Actually, no.
ARM64.
For example, here, so
Or like the public.
AR64,
That
the
actually
official name.
Yeah, yeah.
Oh, it is out.
Oh,
Oh, yeah.
So-
Wait,
Why are you,
A-
how do you know all this?
So ARM64,
okay.
actually, we don't have a name for that, I believe. Yeah, I don't think we have a name for ARM64.
But
Yeah.
like, I have.
The real name is
But it's like
AR.
named-
The official name is AR64.
It's like really easy.
Yeah, yeah. No.
You said,
M32 does not work.
Why?
Oh, yeah, let me show you.
oh, yeah, talking about the company on ARM. So,
Yeah,
so this is M1?
M4. Yeah,
This is
the
M4?
same, yeah.
Okay, okay.
I learned a lot. Like, if you know about like everything in your background, then I'm assuming you.
No, no, about that.
Just Google.
Okay, sure.
Okay,
Yeah, just Google. Yeah.
and then maybe I
You
will
go to,
do
like-
like install cross compile toolkit.
I
I don't think so. I don't think you need to. It should be compatible.
So I live
Okay,
Yeah.
you know?
Should be compatible.
like, it's a place, like, you know where, where,
Yeah.
yeah, I'm like,